Hi, this video is all about aquifers, the water-bearing rocks underground from which we can extract useful sources of water for drinking, for domestic use, for industry. They're a crucial part of what geologists can end up doing as a career. Britain is blessed with several different aquifers that in certain parts of the country are a key water resource to supply the populations living there. Now, the geology map of Britain shows a distinct pattern. We tend to get older rocks in the far north and the west, and younger rocks in the south and in the east. For the aquifers, this is incredibly useful for us, where we get the greatest population densities and also the lowest rainfall and surface water storage capacity. We have the largest amount of groundwater available. A geological accident, but a handy one. The three main aquifers that we use in the UK are the Permian and Triassic sandstones that you can see in the Midlands and North, desert sandstones, well sorted, fracturing, going on to create high porosities, reasonably high yields. The Jurassic limestones that run down through the Midlands, with a lot of secondary porosity and permeability, again can be an important source. And probably the most important of all our groundwater resources, the chalk that underlies so much of the southeast of England. It provides much of the water for London and the southeast. Despite its slightly lower yield, it's a very porous rock, and it is massively important to supply the bulk of the population in that part of the country. The younger rocks then, that provide much of our groundwater resources, tend to be, well, less cemented, perhaps a little more porous, some more limestones in there. Okay. Provide some of the main aquifer resources for the UK. The chalk, the Jurassic limestones, and the Permo-Triassic sandstones. The older rocks that we find more in the north and in the west can provide some local supplies, but generally the permeability is lower, and also because of the landscapes that they create, it tends to be more mountainous, it tends to be wetter, so surface storage in the west and the north is a far greater component of our water supply than groundwater. If we look at aquifers, this is a cross-section. If we look at a cross-section through aquifers, we can see there are several different features. You need to be aware of some of these features. You can see here we have a difference between what we call an unconfined aquifer and a confined aquifer. An unconfined aquifer is open to the surface. So when rainfall falls on those rocks, it soaks straight down to the water table to recharge the aquifer. A confined aquifer has an impermeable layer on top. So the recharge of this aquifer will come from somewhere else. Now, a confined aquifer could end up with water under pressure. This creates a feature we call a piezometric surface. Now the water table that you can see is the level at which the rocks become saturated with water. So below the water table, all the pore space in the rock is full of water. You can see on this diagram that it extends above the surface in a confined aquifer. This is because of the pressure that the water's under. The piezometric surface marks the level the water will get to, it'll rise to, if it's able to escape through the impermeable bed. It does make it easy to pump aquifers like this because the water is already flowing out under pressure. If we expand this diagram a little, this is the diagram you have in your notes that highlights the features that we've already mentioned. There are one or two other terms that you need. Where we have an impermeable sedimentary rock in the ground, we call this an aquiclude because it excludes water. An aquiclude can help to keep water near at the surface, or can confine an aquifer to create a confined aquifer. It's important for us as geologists to understand where beneath the surface we have the porous permeable rocks that can make aquifers and the impermeable rocks that will make aquicludes. There's another term we use as well called an aquitard. Now an aquitard is a sedimentary rock that has fairly low permeability. It may have perhaps more cement. So although water can flow through it, it's going to be slow. We're not going to perhaps necessarily be able to pump that aquifer very much. You need to know the meaning of all of these words on this diagram. Okay, if we want to extract water from an aquifer, which is really what the purpose of this study is about, we need to be able to drill a borehole. Now boreholes vary in diameter, but it's a hole drilled down into the rock, well down into the aquifer. It may go down 1, maybe 200 meters down. They don't tend to go much beyond that because pumping water from depth is very expensive. The top of the borehole will be sealed to prevent contamination from the surface getting down into the aquifer. The borehole itself will be cased with a pipe. Okay. When we actually get into the aquifer then, a slotted pipe called a well screen is lowered to the bottom of the hole. This is a metal pipe that has holes in to allow the water to flow into the bottom of the borehole. That will be surrounded by a permeable material, maybe just gravel, okay, to filter out some of the any solids that might come through before they get to the well. A pump then is lowered down below the water table to actually bring the water back to the surface. Now when a borehole is pumped, one of the consequences of this can be that the water table will be lowered in the area around the borehole. This creates a feature we call a cone of depression. The cone of depression is, as the name would suggest, a cone-shaped area of dry rock where the water table has been drawn down as water is pumped down. Now this occurs where the rate of water being pumped out of the hole, the discharge, is greater than the rate of flow of the groundwater into the well. It can have a number of consequences. Clearly, if the cone of depression gets too big, the borehole will go dry. There won't be any water flowing into the hole. Also, this rock that's now dry below the water table can compact. The result of this can be subsidence of the ground at the surface. This is due to a reduction in the pore water pressure of the groundwater. If we look at an example from the Chalk Aquifer under London, in the summer, with low rainfalls, the water table in the chalk will be depressed around the wells, creating these cones of depression. During the winter, where there might be excess water, perhaps water pumped out of the rivers, like the River Thames, the River Lee, that can actually be pumped back into the chalk to artificially recharge the aquifer. So using the aquifer as a storage reservoir. So, to conclude, aquifers have features that geologists need to understand if we're going to be able to plan for the extraction of useful quantities of water. It's important to know what each of these features are and be able to identify them either on maps or on cross sections so we can understand the flow of that water. Don't forget to come up with your interesting question and bring it along to class. I'll see you then.